It's my first time at CppCon. I've thought about going for a lot of years and now kind of regretting that I didn't go sooner.
Good evening, everyone. My name is Rutvij Karkhanis, and I'm a software developer at Apple. And today, I will be talking about the usage of modern C++ on embedded systems. So we'll be starting off with the basic semantics, class types, namespaces, STL algos, atomic load and store, and then build on to object-oriented techniques. We'll also be covering, going over some of the optimization techniques in C++ for embedded platforms, like using assembly listings, lambda expressions, efficient register accesses, and so on. And finally, we'll take a look at some of the reusable mathematical tools in C++ that can be highly useful on embedded platforms. So let's get started. So class types. Class types enable object-oriented programming in C++ because they group data together with functions operating on them in a self-contained entity. Classes, structures, and unions typically have a mixture of data, functions, and overloaded operators called as members. Let us over here examine a simple point class that encapsulates the Cartesian coordinates for trivial geometric calculations. We have a default constructor over here, a parameterized constructor, and member variables and functions. Typically, the member variables are qualified with private and protected access specifiers for better encapsulation of the data. Here we see examples of overloading the stream insertion operator to be able to print the instance details easily. And similarly, the addition operator is overloaded to perform addition on 2 point instances trivially. In this case, it sort of serves us well to have the member variables as public since the operator overload functions are not members of the class. So now let us look at how we can start using the class types. Just like for basic types, we would need to start by instance creation. Direct list initialization is the modern recommended approach. It uses curly braces. Key advantages of this kind of initialization being it prevents narrowing conversions. It's a compile time error to initialize an object with a value that would lose information. For example, using this style to initialize an int with a float value would fail to compile. This also solves the most vexing parse problem. Point P with curly braces is unambiguously an object definition and not a function declaration. It also works with aggregates. It's the standard way to initialize aggregates like C-style arrays or structures and so on. Namespaces. So namespaces are tools to group related symbols together. They avoid symbol name trampling. C++ also has a concept of unnamed namespace called as anonymous namespace. An anonymous namespace limits the scope of anything that is defined in it within itself to the file level scope. A file local anonymous namespace guarantees unique names for otherwise same named symbols occurring in different files. The anonymous namespace is considered superior to the C-style static. In fact, some developers consider the anonymous namespace to be the preferred mechanism for file level scope localization and reduction of naming ambiguity in C++ projects. In this example over here, we showcase the modern approach of defining a nested namespace. Constant expressions. The const.dxpr keyword can be extremely useful for generating lookup tables. And lookup tables are especially significant in the embedded world. Here's such an example of generating a sign value approximation lookup table. We compute the approximate sign values using Taylor series expansion. Now here's the interesting bit about this code. If we look at the assembly code generated, we see that the sign value lookup table is stored as a constant. These are floating point values over here. These values have been calculated by the compiler and stored as a lookup table. Static asserts. The static assert facility checks a constant expression at compile time. In this code snippet, we demonstrate the use of static assert to check if the element location accessed in the std array object is within range. Here, the expression is a condition to be checked by the compiler, and the message contains potentially useful diagnostic text. If the result of the expression is true, then the static assert does nothing. Basic STL algos. Using STL algorithms in C++ can significantly reduce coding effort and eliminate potential sources of error from handwritten code sequences. It is easy to get started with a few intuitive and easy to use STL algorithms such as std-min, std-max operations, mutating or change-causing sequence operations such as std-fill, std-copy, or any such non-modifying sequence operations such as std-all-off or for each, etc. Instead of arduously developing and testing handwritten containers and loops, the standardized components of the STL can be used out of the box. With the consistent use of standardized containers, iterators, algorithms of the STL, the code will adopt a recognizable look and an easy to understand style. Atomic load and atomic store. The C++ standard library includes a collection of safe and portable atomic operations in its atomic library. These are extremely useful to solve data races and reordering problems. On many systems, writing an integer, for example, isn't a single instantaneous operation. So the consumer side may be at a risk of reading a torn value, resulting in garbage value calculation. The second problem arises when, to optimize code, the compiler or the CPU is allowed to reorder instructions if it doesn't change the logic within a single thread. So in the example above, in the ISR, the compiler might decide that it's faster to set the g_new_data_available to be true before it writes the new value to the g_sensor value variable. The consumer side could then be at risk of reading the stale data. So we use atomic store in this example to perform a consistent write to the variable g_sensor_value and the g_new_data_available in the ISR. Similarly, in the main function, we do an atomic load to read the sensor value previously written in the ISR. Align off and align as. So align off and align as are C++ features that give you control over the memory alignment of the objects. You use align off to query the alignment and align as to set it. Forcing a stricter alignment, for example, a larger power of 2, often adds padding bytes to the struct, which will lead to increase on its size. std span. Now, std span is a fantastic C++20 feature that provides a non-owning bound safe view over a contiguous sequence of objects. It's like a smart pointer for a block of memory, but without the ownership of the block. The primary benefit of std span is that it allows you to write a single function that can operate on data from, for example, an std vector, a C-style array, an std array, or any other contiguous container without templates and without making any sort of expensive copies. So in this example, we see that process data function can be passed any contiguous container, for example, a vector, a C array, or an array, std array object, for the same operation to be performed on the data. Now let's look at some of the object-oriented techniques we can take advantage of for developing embedded systems. Dynamic polymorphism. Dynamic polymorphism is a powerful C++ feature that is highly valuable in embedded systems, especially for creating flexible and maintainable hardware abstraction layers. The core idea is to define a common interface, an abstract class for a type of hardware. For example, in this case, a sensor. Then you can create different concrete classes for specific sensor models that can all implement this common interface. The main application code can then work with any sensor through the base class interface without needing to know the specific details of the hardware that it's talking to. Here in the main application logic below, we create the temperature sensor and the humidity sensor objects on the heap and store the addresses in a pointer of the type which is of the base class interface. Benefits in embedded context, you get decoupling, extensibility, and testability. Decoupling in the sense that the main application logic is completely decoupled from the specific sensor hardware. It only knows about the eye sensor interface. Extensibility in a sense that if you want to add support to any other specific sensor type, for example, like a pressure sensor, you could create a pressure sensor class that inherits from the sensor interface, and you don't need to change a single line of code in the main application logic. And testability, this pattern is fantastic for unit testing. You can create a mock sensor class that returns predefined values, allowing you to test your application logic without needing any kind of physical hardware connection. Now, what would be the cost of this feature? So there's two aspects to this. First is the memory overhead, and second is the performance overhead. So there are two components to the memory overhead, the virtual table, vtable. For each class that contains and inherits at least one virtual function, like the eye sensor class or the temperature sensor or the humidity sensor, the compiler generates a single static array of function pointers. This is the vtable of the class. It holds the memory addresses of the correct virtual function implementations for that class. This is a per class overhead and is generally very small. The virtual pointer, vptr, this is the more significant cost. Every object of a class with virtual functions gets an extra hidden member variable, a pointer called the vptr. The pointer points to the vtable of the class, of that object's class. So what's the impact of this? This increases the size of every object. For example, on a 64-bit system, the size of the temperature sensor class that we saw will be 8 bytes larger than what it would have been if its methods were not virtual. While this may seem negligible for a few objects, it can quickly add up and become significant if you need to create millions of small polymorphic objects in a system with a small RAM. Second is the performance overhead. Now, a non-virtual function call resolves at compile time. The compiler knows the exact memory address of the function to call and generates a direct jump function instruction. This is extremely fast. But for a virtual function call, when your code calls, for example, in the previous example, the read function using the member access operator on the sensor underscore PTR pointer, base pointer, it needs to follow a certain number of steps. So first, it needs to follow the sensor PTR to the object on the heap. Then it needs to read the object's hidden vptr to find the address of the vtable of the class. Then look up the address of the read function within the vtable. This is typically a fast lookup since it's a fixed offset. And then after that, call the function at the retrieved address. So when non-copyable classes. So when using non-copyable classes, the compiler will issue an error for any code, including compiler-generated code, that tries to copy the class. A class is made non-copyable by declaring the copy and the move constructors and the assignment operator as private and qualifying them with the delete keyword. This technique is done on purpose to eliminate the risk of both intentional as well as unintentional attempts to copy the instance of a class. If only one instance of a class should be allowed to use a single resource, then non-copyable semantics can reduce the risk of unintentionally using the resource with multiple instances of the same class. Constant functions. When you add constant keyword after the parameter list of a member function, you are telling the compiler two things. A promise that this function will not change any of the member variables of this object, and second is the ability that this function can be called on constant objects. Sometimes a class has a member that you want to be able to change even from within a constant method. This is usually for internal bookkeeping, like caching or instrumentation, that doesn't really affect the logical state of the object. In such cases, the member is marked as mutable. This tells the compiler that allow this specific member to be modified, even inside a constant member function. This is a powerful feature when you need to break the constant promise for a very specific justifiable reason. Friend classes and functions. The friend keyword is used to grant specific external class or function special access to the private and protected members of the class that declares them as a friend. It essentially creates a controlled exception for the rule of encapsulation. The primary purpose is to allow two or more tightly coupled classes to function or functions to work together efficiently without forcing you to make the class's internal state as public, which would break encapsulation for everything. In this example, a friend class sensor monitor that acts as a diagnostic tool for temperature sensor class can access the private members of the temperature sensor class. The reset sensor calibration global function is a friend function of the humidity sensor class that can access and modify the private calibration data of the humidity sensor class. Friend qualification should be used sparingly though. It is a powerful tool, but it intentionally weakens encapsulation. Before making anything or a friend, always consider if there's a different design that could achieve the same result by using the class's member interface, class's prior public interfaces. Template functions. Template functions are used to write generic reusable code that can work with different data types instead of writing separate functions for, say, int, double, or strings, etc. You write a single function, which is a blueprint, a template function, and the compiler generates the specific version needed for each type that you use with it. The primary goal of using template functions are code reusability, write the logic once and use it for many types, type safety. The compiler checks types at compile time, preventing errors that might occur with less safe alternatives like the void star pointer. And performance. Because compiler generates specialized code for each type, there is often no runtime performance penalty. This is the key advantage over dynamic polymorphism using virtual functions. In the call to the function add, in this example above, the template parameter is not explicitly given. The compiler can automatically deduce the type of the template parameter if it has sufficient information to do so from the context of the usage. This is via the C++ 17 feature, the C tag. Template class types. Similar to template functions, template classes are used to create blueprints of classes. It achieves the same primary goals as we saw with template functions. In the example above, instead of writing a separate class for every possible data type that you might want to work with, for example, the class could be point int or point float or point double. You write a single generic point class template with t passed in the angle brackets as the template parameter. The compiler then uses this blueprint to automatically generate the specific class you need at compile time. Now let's talk about CTAD. Class template or argument deduction is a major C++ 17 feature that dramatically simplifies the way we create objects from class templates. Before C++ 17, when you wanted to create an object from a class template, you almost always had to explicitly specify the template arguments in angle brackets. CTAD allows the compiler to automatically deduce those template arguments from the arguments that you pass to the constructor. Static polymorphism. Now, static polymorphism is a powerful C++ technique that achieves polymorphic behavior at compile time, primarily through templates. Unlike dynamic polymorphism, which uses virtual functions and pointers to resolve calls at runtime, static polymorphism resolves calls during compilation itself. This means there is no runtime overhead, no vtable lookups, and allows for better optimization like inlining. The core idea is duck typing. If it walks like a duck and quacks like a duck, it is a duck. If a type has methods a class template expects, then it can be used with that template. Some characteristics of this type of programming are, there is no base class or virtual functions. Compile time resolution. When you call, for example, in this case, the process sensor with temperature sensor as the argument, the compiler generates a specific version of that function for the temperature sensor type. Third is there is no runtime overhead because there is no vtable or vptrs. But there's also a caveat, which is the loss of runtime flexibility. The main trade-off being that you cannot store different sensor types in a single homogeneous container as you could previously. Variadic templates. Variadic templates are used to create functions or classes that can accept a variable number of arguments of different types. This allows you to write highly flexible and reusable code that isn't tied to a fixed number or type of parameters. The primary use cases include generic utility functions, creating functions like type safe printf, a logger, or an argument forwarder that can handle any set of inputs, factories and constructors, writing functions that can construct any object by forwarding a variable set of arguments to its constructor, and metaprogramming. Metaprogramming performing complex compile time operations on list of types such as a tuple, a variant, etc. Template metaprogramming. Templates can be used to offload computation work efficiently to a compiler rather than doing the computation in runtime. That's what's achieved by template metaprogramming. Here we introduce a recursive template metaprogramming example using factorial function. The template metaprogramming uses templates to do the work at compile time that may otherwise need to be done during runtime. Template metaprogramming can be useful for sophisticated optimizations such as compile time generation of constant values, loop unrolling, and etc. Here we can see in the assembly listing that the value of the factorial is computed by the compiler, the value 120, and stored in the code section of the executable. Contrasting that with the regular iterative example of the factorial function, we see that the number of instructions to compute the factorial in runtime drastically increases. Type traits. In simple terms, type traits answers questions about a type before the program runs. In the snippet example, the function makeLarge is designed to combine two smaller unsigned integers into one larger unsigned integer. For example, two UN16s can be combined to make a UN32. Type traits are used here to add compile time safety checks. So the std is underscore unsigned : value. This trait checks if the given type is an unsigned integer. The line static assert std is underscore unsigned u short ty : value, and with the message u short ty must be unsigned type, tells the compiler that before you even try to compile this function, check if the u short ty type is unsigned. If not, then stop the compilation and show the error message. This prevents a developer from accidentally calling the function on signed integer types like int or long, etc. And other signed types which would lead to undefined behavior with bit shifting signed integers due to sign extension. The error message is clear over here and it's immediate. Without type traits, you would either have to rely on runtime checks, which are slower and less safe, or let the compiler produce potentially confusing and lengthy error messages when a developer uses the wrong types. Type traits allows you to express your intent and enforce it directly at compile time. Variable templates. Variable templates can be particularly useful in generic numeric programming. Consider this non-trivial Stirling's approximation of gamma function included in a variable template function. Here we can call the function for different types like float, double, long double, etc. to get different precisions of the result. In this example, we return a safe default value for a particular type. We use the if constxpr expression introduced in the CPP17 to select the default value at compile time. We use a lambda function over here to return the default value for arithmetic types like int, float, double, pointer types, and non-arithmetic or pointer types like string. SFI, NAE, and enable if. So the std enable if is a library-based technique that cleverly exploits the compiler rule called SFI NAE, substitution failure is not an error. How it works: if a template substitution results in an invalid type, like trying to access the : type from the std enable if when its condition is false, the compiler simply discards that function overload and instead of producing any error. Here we use std enable if, and std is integral to restrict a template function to integral types only. The syntax for this is notoriously verbose and difficult to read, often referred to as template metaprogramming boilerplate. The biggest drawback for this is error messages. When constraints aren't met, the compiler doesn't say that your type T is not an integer. Instead, it produces long pages of cryptic error messages about template substitution failures, making debugging very difficult. Concepts. So C++20 concepts are a direct superior replacement for std enable if. They solve the same problem, which is constraining templates, but in a way that is very vastly more readable, expressive, and is also user-friendly. How does it work? You define a named set of requirements, that is a concept, and the compiler checks if a given type satisfies those requirements. The syntax in this case is clean, intuitive, and directly expresses the intent of the programmer. In the example here, we define the concept integral and directly use it in the function, versus in the previous example, the enable if checks the type and then assigns the return type to the function, the syntax for which can be pretty verbose. Now let's look at some optimizations that we can perform for C++ on embedded platforms. Compiler optimizations. Here we benchmark a computationally intensive code sequence rich in 32-bit operations implementing a CRC32 cyclic redundancy check. When benchmarking the CRC32 program for speed, 2 runs were made with optimization settings for O2 and O3. The space optimized run used the optimization setting OS. For the GNU C++ compiler, the optimization setting O2 performs most available optimizations that do not strongly increase the code size. Optimization setting O3 performs all of the optimizations of level O2 plus additional potentially expensive optimizations such as inlining of functions, loop unrolling, loop distribution, that basically increases the code size. Using assembly listings. Assembly listings allow us to follow the original high-level C++ source code into the intricate depths of the compiler-generated assembly language and machine-level opcodes. Revisiting our factorial example, we use the obj dump tool to disassemble the object file to create the assembly text file over here. Map files. Map files are incredibly useful for understanding exactly what the compiler and the linker have produced. Considering the previous example for dynamic polymorphism, from the map files, we get a clear insight into the vtables for each of the class. Each of these symbols represent a static read-only array of function pointers that the compiler places in your final executable. When you create an object like temperature sensor, a hidden pointer inside that object, the VPTR, is set to the address of its corresponding vtable. And this is how a call to specific sensor object functions can be resolved to the correct function at runtime. This would be a good opportunity to compare some of the contents of the map files for the static polymorphism versus the dynamic polymorphism examples that we saw earlier. So the first thing that we observe is that the code size for dynamic polymorphism increases by a lot compared to the static polymorphism attributed to virtual functions and the VPTRs. Then we have the vtables present in the dynamic polymorphism case versus the static polymorphism case. Then we also have the runtime type information present for dynamic polymorphism case. We also use the heap, and also the complexity is pretty high with the dynamic polymorphism case. Name mangling and demangling. In order to guarantee non-conflicting symbol names in C++, the compiler needs to make decorated internal names for variables and subroutines using additional information based on partial names of parameters or namespaces or classes, etc. In practice, the names that a C++ compiler makes can be so long and difficult to read that the name decorating process itself came to be known as name mangling. With specific tools like the C++ filth program, it is possible to demangle the mangled names created by the compiler. Utilizing the ROM efficiently. Embedded systems often have very limited RAM, and in this situation, it is apt to organize the program data to account for efficiency. Here we see a conceptual linker file. It starts with the entry point of the application. This is typically the startup function for the specific embedded platform. Then we have the memory block. It explicitly defines the flash region starting at 0x8 million. This is our ROM. And here we also see the RAM section of the platform. The text section, it places all the executable code in the .text and all the read-only constants, the RO data, into the flash region. This is the most direct use of ROM over here. The eText symbol is created to mark the end of this section in the flash. The .data section, this is the clever part. The angle bracket SRAM, this says the section will run from the RAM. Its virtual memory address, the VMA, is in the RAM. The @angle bracket flash, this says the section's initial values should be loaded into the flash. Its load memory address, the LMA, is in the ROM right after the text section. The _SI data symbol is created to mark the location of those initial values in the flash. Custom memory management using the placement new. So placement new is a special version of the new operator in C++ that allows you to construct an object at a specific pre-allocated memory address. Unlike the regular new operator, which both allocates memory and constructs an object, placement new only performs the construction step. This is particularly useful in performance critical applications, embedded systems, or when implementing custom memory management schemes where you need precise control over where and how the objects are created. In this example, the management of memory buffer is left to the user. Lambda expressions. So Lambda expressions offer the compiler more opportunities to optimize by making the function, its iterator range, and its parameters visible to the compiler within a single block of code. In this way, the compiler has access to a richer set of register combinations, merge possibilities, etc., and it can do a better optimization job. Using Lambda expressions consistently throughout the entire project can save significant code and generally improve the performance of the whole software. Registered accesses. So register addresses can be easily defined as compile time constants. In this snippet, we use the const_expr, which guarantees the address is a compile time constant, allowing for optimizations. And the type is the unptr_t, which is the correct integer type for holding a memory address. Here we see the register access handler class. A new template class is introduced to manage the register operations for a peripheral at a given base address. It is constructed with the base address of the hardware peripheral, for example, a GPIO base address. You have the masked register write template function. This function implements the classic read, modify, write sequence safely. It takes the register's offset, a mask to specify which bits to change, and the value to apply. Using a volatile pointer ensures the compiler performs each step exactly as written, which is critical for hardware interaction. Then you also have the mass register read template function. This function reads the register and immediately applies the bit mask to it, to the value read, and returns only the bits that you are interested in. Startup code using C++. The microcontroller startup code generally has to handle several key things before calling the main routine, namely initializing CPU registers, power domains, timers, interrupts, ports, etc. Initializing data in the BSS section, initializing all the static constructor instances used in the program, etc. The static class type instance construction is handled via compiler generated functions, which have highly mangled names. The addresses of these compiler generated subroutines is stored in special linker section. Different compilers use different namings for this section, containing the constructors. The sections names can be like ctor inits or init array, etc. These sections need to be looped through, and those functions need to be called in order to construct those static instances before the main runs. Static initialization considerations. So C++ provides certain guarantees when it comes to static instances. All of the non-subroutine file local statics are guaranteed to be initialized before any function inside that file uses them. But C++ supports file translation, and there is no rule to govern the order of initialization of statics in different files. After separate compilation of different translation units, the linker is free to combine the object files in any order it deems efficient or convenient. This can lead to program crashes due to what is called the static initialization order fiasco, where a static is accessed before it is constructed. This is remedied with a modern C++ pattern called the Myers-Singleton instance pattern. In this example above, the subroutine local static logger instance inside the getInstance function below is a function local static variable. It is not constructed when the program loads. It is constructed and initialized the very first time the getInstance method is called. Multithreading in C++. The C++ standard library for threads is an abstraction layer. It needs a scheduler and synchronization primitives provided by an OS to function. You are most likely to find full or partial support for the thread library when your development environment is built on top of a modern RTOS that explicitly provides the necessary C++ bindings. These include Zephyr OS, RTOS, Embed OS, FreeRTOS, etc. Creating C++ wrappers around native RTOS APIs is the most prevalent pattern that you go for. You use the RTOS's native C functions, like, for example, xtaskCreate in FreeRTOS, but wrap them around your own C++ classes to get the benefits of RAII. In this example, we have the iRunnable abstract base class, which defines a pure virtual function, void run. This creates a common contract that any runnable class, any runnable task must fulfill. The FreeRTOS task class provides a clean object-oriented way to manage tasks. It uses a common C++ pattern called CRTP to bridge the gap between the C-style function pointer, the task underscore entry underscore point underscore trampoline, and the C++ member function run. This allows each task to be a self-contained object within its own state, with its own state. Now let us look at some of the reusable mathematical utilities in C++ that can be adopted for developing embedded systems. Floating point math. Some microcontrollers have hardware support for floating point arithmetic using an FPU. An FPU can make floating point arithmetic as efficient as integer calculations, or even more so in some cases. Many small to medium microcontrollers, however, do not have an FPU, and the floating point calculations are performed with a software floating point emulation library. Mathematical constants. So C++20 adds a wide collection of common mathematical constants such as square root of 2, pi, log 2, exponent e, etc. and in the numbers header file. Complex values. The C++ standard library supports complex valued mathematics with its template data type, std complex. The std complex data type is defined in the complex header and specified only for built-in types such as float, double, long double, etc. The public interface for std complex class supports basic arithmetic operators, elementary transcendental functions, the norm, polar coordinates, etc. In the above example, we perform these operations on the complex numbers. More non-trivial operations can be performed on complex type, such as implementing fast Fourier transforms, FIR or IIR filters, etc. Fixed point math. Embedded systems without the FPU support would have a large performance penalty to perform floating point math. So those calculations are get replaced with fixed point calculations. A fixed point number is an integer-based data type representing a fractional number having a fixed number of integer digits to the left of the decimal point and another fixed number of fractional digits to the right. So in this example above, we define a fixed point type to perform mathematical operations on fractional data. We use a 64-bit integer with 32 bits for fractional part, represented with the Q notation, and you write it as Q32.32. Let's talk about representation over here. The fixed point class wraps a standard integer type, the int64 underscore t in this example. This integer holds a scaled value. What is scaling? A scale factor of 2 to the power 32 in this case is used to convert between the floating point number and internal integer representation. For the purpose of addition and subtraction, these are the simplest operations because both numbers have the same scale factor. Their underlying integer value can be added or subtracted directly. But in case of multiplication, when you multiply the two fixed point numbers, their scale factor also gets multiplied and it becomes by the power of 2. The result is scaled by s, for example, s squared. So we must divide by s by right shifting to bring it back to the correct scale value. A wider integer type, in this case the int 128 underscore t, is used as the intermediate calculation to prevent overflow. In case of division, to maintain precision during the division operation, we do the opposite of what we do in multiplication. We pre-scale the numerator by the scaling factor by left shifting before performing the integer division. This ensures the fractional part is not lost. Now, this brings me to the end of our talk, and can open up for questions.
Hello. So when you mentioned about, not all platforms, especially embedded platforms, will have access to a threading abstraction, especially not standard thread. Have you found any benefit in making like a standard compatible thread abstraction for a particular real-time operating system? Or has it been like too much work or not worth it for most applications?
Yeah, so typically, I've worked with the C++ abstraction. So I found it worthwhile to essentially be able to use testing patterns, unit testing, and so on. So that essentially gives you an advantage in that respect. So yeah, it mostly is advantageous to use abstractions.
Okay, thanks.
So I'll be releasing these slides on the Discord channel, as well as the code snippets that I've used on a GitHub link, which I'll post on the Discord channel as well.